This video is on section 12.2 in your book, Inference for a Single Proportion. 12.1 was on inference for a single mean. So we've done means, we're doing proportions. Inference here, broadly speaking, means confidence intervals and significance tests. So section 12.2 deals with both. You've already done some confidence interval work with proportions. It'll be repeated to a small degree here, but most of the focus will be on significance testing for a single proportion. There are a few subtle differences in the condition checks and the calculation of the standard error for proportions, a few subtle differences between confidence intervals and significance testing. So pay attention to that as we go through. Let's start with this for the heck of it. Can you name Minnesota's 2 U.S. senators? Well, how'd you do? Al Franken on the left, Amy Klobuchar on the right. Let's say, in fact, the proportion of Americans who can actually ID their senators is 30% or 0.3. We've made this up. I have a hunch that's high, unfortunately. Let's say we take a random sample of, let's say it's 100 Eden Prairie students, and we find that 38 of them can actually ID their senators. We might ask the question, is there evidence that we do better, worse, different than the rest of America here at Eden Prairie High School? Well, you should recognize this is there evidence language as significance testing language. And so this is asking whether there's a difference between what all of America can do in terms of identifying senators versus what we can do at Eden Prairie High School, where 0.38, the sample proportion that can identify it as 0.38, or 38 out of 100. Now, it's a similar question to what we've done with means. Is there a difference between a statistic and a parameter? And we tested that with null and alternative hypotheses. So one of the things you'll have to do is you start reading multiple problems as distinguishing between questions about proportions and questions about means. This is about proportions. And the null here would be that there is no difference between folks at Eden Prairie High School and folks nationally. But the alternative here was about whether we're different. So that's a not equal to case. So again, we can use hypotheses with proportions just like you did with means. And the real question then is 0.38 significantly different than 0.3, significantly different enough that it would cause us to say, yes, there's evidence in favor of the alternative here. Well, to do that, math, we're going to need a test statistic, which in this case will end up being a z-score. We're going to need a p-value to do the hypothesis test, which would be, in this case, it would be 2 times the probability that we get a p-hat greater than or equal to 0.38. And it's 2 times because it's a two-sided or two-tailed test. So again, as I said, the rhythm and the logic here is similar, but some of the details are changing. So for proportions then, we're going to need a z-score. And while it's not x bar and mu, the pattern is the same here. We have some estimate minus a null value, so p sub 0 here is the null value, divided by a standard error, p times 1 minus p over n. But again, notice we're using the null value here. And in general, when trying to figure out what p to use in a standard error calculation, the safe thing to ask yourself is, what is the best p I have at the moment? And until proven otherwise, the best p we had was the null value. We haven't proven yet that Eden Prairie High School is different than that, so that's the best p we have. So in a significance test, in the standard error of p hat, the denominator here, we're going to use the null value, and that's important to remember. We're going to distinguish that from the confidence interval. We've done this before, so a confidence interval is an estimate p hat plus or minus z star, which is a certain number of standard errors, and you'll notice here we have p hat. So in the standard error calculation here, we're using p hat because that's the best p we have. The purpose of the confidence interval is to estimate p, population proportion. We don't know what p is, that's why we're estimating it. So at this point, the best p we have is p hat, and we'll use that in the standard error. In the 12.1 videos, I showed you these two formulas. These are off the formula sheet. And again, this is how the test statistic and the confidence interval are presented to you generically. And then within the body of that formula sheet, you'll see this as the standard error or standard deviation. And so you need to know that if you're doing a significance test, the null value goes in for P, but if you're doing a confidence interval, P hat goes in for P. And this becomes the standard deviation of the statistic in both of these formulas. Now, from this point on, the logic is very similar to what we did with means. We're going to work with the assumption that we have a normal distribution, and it's the sampling distribution of all the p hats that might have been gathered from samples of the same size from the same population. And the mean of those p hats is p, so the center of our distribution is p. And we have a standard deviation or standard error, p times 1 minus p over n, with p hat or p sub 0 substituted for p. We calculate a p hat, and then under the assumption here that we have a left-tailed, or excuse me, a right-tailed test, p is greater than some value, then we use normal CDF, or we'll use the function on our calculator to calculate the p-value, which is the probability of getting that particular p hat value or higher. Similarly, we can convert p hat to a z-score. We can get a test statistic, and we can calculate that p-value using the test statistic. That's the same logic that we used when dealing with means. Then we're going to compare that p-value to some alpha, and I'm depicting a case here where alpha is greater than the p-value. And that cutoff for alpha, the z-score that goes right there, that's the critical value, so that's a z-score, which is a critical value z-score that chops off a tail of size alpha. So again, we're going to compare p-value to alpha, and we're going to reject or fail to reject the null. In this case, I've depicted a right tail test where the p-value is smaller than alpha, and we would reject the null. Again, the rhythm stays the same. We're going to go through a simple random. We need a simple random sample. You need to start remembering, not be robotic about it. The purpose of that is to be able to generalize to a larger population. And if we don't have a random sample, which may be the case, then we want to indicate that we need to be careful generalizing. Independent observations here, the rule of population being greater than or equal to 10 times the sample size. Again, that's a rule of thumb. Tends to work well for polls and surveys, but there might also be an argument of logic. And if independence doesn't exist, or if we're concerned about it, we should point that out. Now, normality is a place where subtleties occur here, so it's important you understand that what we do for confidence intervals and what we do for significance tests is just slightly different. In both cases, we're going to consider n times p and n times 1 minus p greater than or equal to 10. But again, when dealing with a confidence interval, we don't know p, so we're going to use the best p we have, which is p hat. In significance testing, then, again, it's going to be n times p and n times 1 minus p greater than or equal to 10, but the best p we have is the null value. So this p sub 0 here indicates our null value. So the p we're going to use there comes from the null hypothesis. That's an important detail for which you will be docked if when checking conditions you don't pull in the right p. So use the best p available. Lastly on this slide, something that students figure out after a while is that if you do n times p hat and n times 1 minus p hat, those are actually successes and failures from our binomial deck. So while you can continue to do n times p hat and n times 1 minus p hat for confidence intervals and be sure you're doing things correctly, you can also simply quote number of successes and failures as being greater than or equal to 10 and save yourself just a few seconds of work. Another thing students tend to confuse here, I want to point out, is the difference in mean and standard deviation when dealing with proportions, what I've been talking about in this video, and dealing with counting things. So when we're dealing with a null value about proportions or a problem about proportions, your mean and standard deviation calculations are on the left. But back to the binomial math we did earlier, binomial math was about counting things, number of successes in a certain number of trials. And in that case, our calculations were different. And sometimes when we're going quickly, we forget that. So the hypothesis testing and the confidence intervals we're doing, we're working on the left side of this diagram. But frequently on an AP test, you'll see confidence interval significance testing questions mixed in with things that are about counting successes. And you have to be careful to pull in the right mean and standard deviation at the right time. There are calculator functions on your 84 and 89, one proportion z test. Here are the instructions as you work through examples and work through homework. You might play around with these. Key pieces of data you'll have to enter, the null value as a decimal. Should be obvious, but we're dealing with proportions. Number of successes, number of failures. Those are counts. And you might think of x over n as p hat. So you're entering in two counts that are in fact the calculation of p hat. So when you see x and n on your calculator, think of x as the numerator, think of n as the denominator. Then you'll choose the correct hypothesis, and just like we had with means, the test statistic and p-value will be kicked out. It'll also kick out p hat for you if you want to have the calculator calculate that. So you'll see that when you play around with those calculator functions. Lastly, concluding slide here, we're starting to pile up inference procedures. These are tools in the toolbox, and which tool you pull out depends on the question being asked. So we have several tools now for confidence intervals. And we also have several tools now for significance testing. And we'll continue to add to this list. In Chapter 13, we'll add at least 2 to each of these lists. And in Chapters 14 and 15, we'll continue to add to this. So it's important now that you be able to recognize the question, be able to recognize when it's about means, when it's about proportions, whether I know sigma or not, and so on. So that you pull the right tool out of the toolbox at the right time.